All right, so A5, right? So if we read through the problem, we're looking at the isothermal expansion of a monoatomic ideal gas at 302 Kelvin, right? It's going to be 1.5 moles, right? It's going to be reversible. We're going from 1 liter to 6 liters in a system. And so what we're being asked to calculate, right, is Q, W, delta H, delta E, delta S of the system, and delta G for what we have. So the way that we approach this, right, is that we know that this is going to be, a reversible process. In this case, we know it's going to be isothermal. So knowing all of those things, right, we know that delta E is equal to 0, right? And that means then that Q is going to be equal to negative work, right? Or, alternatively, right, work is equal to negative Q. In these cases, the other things that we know, right, is that because we're isothermal, we're at constant temperature. That means that delta H is also equal to 0, right? Because what we're talking about here is an isothermal expansion compression, right? We're not talking about a reaction or anything like that, right? We're just simply talking about a gas expanding or compressing. And so in those cases, right, delta H is always going to be equal to 0 in those scenarios. Right, so we have that. And so then that means, right, since we know that delta G is equal to delta H minus T delta S in those cases, right, if delta H is equal to 0, right, then that means then that delta G is simply equal to negative T delta S. And so the other thing, right, that we know in this case, right, that delta S is going to be equal to, what is the equation? NR natural log of V2 over V1. Right, and then in terms of work, right, we know that work in this case is going to be equal to negative nRT natural log V2 over V1 in these cases. So, those are the things to think about and to approach. So, yeah, so we have all of these factors and values right here. So now, the thing to consider. So I already jumped ahead of part A, right? So part A is just simply drawing the qualitative MO diagram. So if we take an axis, right, we have pressure, right? We have volume in these cases. And so we're doing PV work, right? We're going to be doing isothermal reversible expansion, right? So that's going to have a curve to it, right? And it has that curve, right, because it's a reversible process, right? If it was an irreversible process, right, it would just simply be like drop down, move over, right? It'll be like very blockish looking. Whereas for a reversible, right, it's just a very gradual change, right? So this is right, our starting point. Or actually, sorry, we're going from 1 liter, which is down here, to 6 liters, right, which is up here. I know. What am I doing? Yeah, sorry. Yeah, right. So we're going from a higher volume to a lower volume, or sorry, from a lower volume to a higher volume, right? But that means then the pressure has to go down in that case, right? Because if the volume's going up, the pressure has to go down, right? This is pretty ugly, but you guys get the gist, right? So that's going to be that right there. And so then in terms of, right, the work, right, that's just going to simply be all of that right there. That's going to be happening, right? Because you're just simply integrating, going from one point to the other. So back to part B, right, where we're calculating stuff. So now all we have to do, right, so we already know a lot of this information, right? So in terms of the number of moles, right, we're given that info right here. We already know what V2 is, right? We already know what V1 is. And R is just simply the ideal gas constant in these cases. So we can just simply plug all of those in, and we should be able to calculate what the result is. So doing that, first things first, work. Right, is going to be equal to negative nRT. I already have it written right there, so I'll just use this. Right, we have this right here. So if I just plug in my value, so I have negative, right, 1.50 moles times R, right? So I'm saying that this is a monoatomic ideal gas. So that tells me, or actually that doesn't matter in this case, right? I don't need CP or CV, right? So it's just simply R, which is the ideal gas constant. So that's 8.314 joules per Kelvin moles times the natural log of V2 over V1, right? So the final volume is 6 liters over 1 liter, right? So moles cancel. Liters cancel, so that way we end up with, oh, I forgot the temperature. I'm jumping ahead of myself. Right, temperature is 302 K. Right, and then we have natural log of V final, which is 6 liters over 1 liter in this scenario, right? So Kelvin cancel as well, right? Liters cancel. And so we just end up with joules, right? Which is the unit that we would want for work. So we have that right there. So we plug all of this in. So we have negative 1.5 times 8.314 times 302 times the natural log of 6 over 1. What we get is negative 6,748 joules, right? Pretty close to what I have, right? I have negative 6,750 joules on the answer key, right? So that's the amount of work that we have. We know then that Q is equal to negative work. So that will just simply be negative of negative 6,748 joules, right? So that comes out to being positive 6,748 joules, right? So that's Q. We already have delta E, so that's done. Delta S of the system, right? All we have to do is just simply plug in the info that we have here too as well. So we can just simply do that. So that's going to be equal to the number of moles, right? So that's 1.50 moles times R, which is 8.314 joules per Kelvin per mole, times the natural log of V2 over V1. Excuse me. Right, so what we get there is, or sorry, V2, which is 6 liters over 1 liter. So what we get there is 1.5 times 8.314 times the natural log of 6 over 1. So what we get is 22.35 joules per Kelvin, right? And so, right, delta S is always going to be in joules per Kelvin, right? Those are always going to be the units that you have for delta S, right? Which matches, essentially what I have on the key as well, right? So that's what delta S is. You could have also made it easier on yourself. You could have just simply done Q over delta T, or not over delta T, Q over T, right? Because, looking at the relationship between delta S and work, right? They're pretty much the same. The only difference is just simply the temperature and stuff. So we have that right there. And then delta G, right? We know the value is up here. So all we have to do now is we take this and then subtract, delta G is going to be equal to negative T delta S, right? So the temperature is 302 Kelvin times delta S, which is 22.35 joules per Kelvin, which comes out to being, right, negative 302 times 22.35 comes out to being exactly the same as the work, right? And that's what, the delta G really is, right? Is just simply the maximum work that can be accomplished by something. Right, and so that's what you get there for the delta G, right? So that all makes sense. Yeah, right. And so in terms of like the slight differences between delta G and Q and work and everything like that, right? I mean, those are all just simply, on the key, probably just like slight errors in terms of sig figs and stuff like that. But that's how you approach that problem, right? And that's how you have to think about and again work your way through. So again, like identifying what are the keywords, what are the things that really guide you in those scenarios.